8086 has a 16-bit flag register, 7 bits of which are undefined or unused, and the remaining 9 bits serve as the flag bits. There are two types of flags in 8086. The condition or status flags, which are 6 in number and are shown with the blue circles. The ones in the gray boxes are the control flags, and they are 3 in number. The boxes with the X signs are the undefined bits. Condition flags are set to either 1 or 0 after a certain arithmetic or logical operation is carried out by the microprocessor, whereas the control flags are used to control certain operations of the microprocessor. There are 6 status flags, and starting from the least significant bit of the register, we have the carry flag, parity flag, auxiliary flag, zero flag, sign flag, and overflow flag. Overflow flag is the only flag that 8085 does not have and 8086 does. Here are a few descriptions of each of the flags. Using a small assembly language, we are going to demonstrate the status flags. Let's say we want to add two numbers given in hexadecimal, 50H and 32H, which are both in the AL and BL registers respectively. We are going to add the two numbers and store the result in AL, as it is the destination register in this case, whereas the BL is the source register. Our first step would be to convert the hexadecimal numbers 50 and 32H to binary, after which we add them. The ones above here indicate the carry bits from the arithmetic addition. For example, 1 plus 1 is 0, carry 1, and henceforth. Now the answer here is equivalent to 82H, and we are going to use this answer to determine the values of our various status flags, starting with our 0 flag. What is our 0 flag? Our 0 flag is equal to 1 if our answer is 0. Otherwise, it is reset to 0 if our answer is not 0. Confusing maybe, but here the answer we got from our arithmetic operation is 82. Therefore, our 0 flag is going to be reset to 0. Sign flag tells us if the answer is a negative number or a positive number. How do we know if the answer is negative or positive? We look at the most significant bit. If it's 1, that means it's a negative number, and if it's 0, it's a positive number. If the MSB is 1, the sign flag is set to 1, otherwise is 0. Now, since in this our case, the most significant bit is 1, indicating a negative number, our sign bit is also set to 1. Carry flag tells us if we have a carry out from the most significant bits. An easy way of knowing if you have a carry out is if, for example, you're adding two 8-bit numbers and you get a 9-bit answer, then you definitely have a carry out. In this case, we are adding two 8-bit numbers and our answer is also 8 bits. Therefore, our carry flag is going to be set to 0. You can see here also 1 plus 0 is 1 and there is no carry out. Therefore, our carry flag is 0. Next up is parity flag. Parity flag tells us if the answer has an even number of ones or odd number of ones. If it has an even number of 1, then parity flag is set to 1. In our answer here, we have two ones. Therefore, our parity flag is going to be set to 1. To determine the value of our auxiliary flag, let's first understand what a nibble is. Nibble refers to a set of 4 bits, and in this case, all the numbers have two nibbles, that is, the lower nibble and the upper nibble. Now, Auxiliary flag is set to 1 if there is a carry from the lower nibble to the upper nibble, that is, from bit 4 to bit 5. In this case, however, 0 plus 0 is 0 and there is no carry. Therefore, auxiliary flag is reset to 0. Overflow flag is used for signed operations, whereas carry flag is useful for unsigned operations. For example, when we are adding two positive numbers, we are always going to get a positive number. However, if the result indicates otherwise, then overflow flag is set. Also, if we are, let's say, using two negative numbers and we get a positive answer, then that also means overflow has occurred. In this instance, for example, we have two positive numbers, but the result is negative, meaning overflow has occurred. Another way to determine if overflow has occurred or not is by simply determining or considering these two most significant bits. If there is a carry from the 7th bit to the 8th bit or carry from the 8th bit outwards, then overflow has occurred. However, if there is a carry from both 7-bit to 8-bit and 8-bit outwards, or no carry at all from 7-bit to 8-bit or 8-bit outwards, then no overflow has occurred. In this case, there is a carry from 7-bit to 8-bit, but there is no carry from 8-bit to the 9th bit or outwards. Therefore, overflow is set to 1. Let's quickly look at another example. Assuming we want to add two numbers FFH and 1, we first convert them in binary and then we add them. As you can see, the numbers given up here are the carry bits, and this is the final result of our answer. To determine our status flags, we only consider the 8 bits because we are adding two 8-bit numbers and we expect our value to be 8 bits. Now the first bit we consider, or the flag we consider, is 0 flag. The answer we got is equal to 0, therefore our 0 flag is set to 1. Next on, we consider the sign flag. As I mentioned, you consider the most significant bit of our 8-bit answer, which is 0, indicating a positive number. Therefore, our sign flag is also 0. Next, we have the carry flag. Since there is a carry from the 8-bit to the 9-bit, that means we have a carry flag. Remember, we added two 8-bit numbers, but our result gave us a 9-bit answer. That is why carry flag is set to 1. We then consider parity flag. Here we have no ones, indicating an even parity. Therefore, parity flag is set to 1. Auxiliary flag, if there is a carry from the lower nibble to the higher nibble or from the 4th bit to the 5th bit, then we have auxiliary flag set to 1. In this case, since we have a carry from the lower nibble to the higher nibble, auxiliary flag is set to 1. Overflow, we have both carries from 7-bit to 8-bit and 8-bit to 9-bit. Therefore, overflow flag is set to 0. Control flags are used to regulate certain operations of the microprocessor. The trap flag is useful for debugging purposes and it's used to execute the program one line at a time, thereby allowing programmers to easily find out the mistake in a certain line of program. Interrupt flag, when set to 1, allows the microprocessor to accept maskable interrupts. Otherwise, if set to 0, it ignores interrupts. Direction flags are useful for string operations. When set to 1, the microprocessor reads memory locations from the higher order to the lower order. And if it's set to 0, then it reads lower memory locations to higher memory locations. With this, we come to the end of flags. Let's try to answer this simple quiz question. Given this set of program, can you determine all the status flags of the 8086?